Hey everyone, and welcome to today's Explainer. We're jumping right into the absolute engine of the global web, Intra-AS routing and the internet backbone. We're going to take a technical, behind-the-scenes look at how data actually navigates the globe and the protocols holding this whole shebang together.
Here's a quick roadmap for us today. First up, the network of networks. Second, BGP, the global diplomat. Third, the mechanics of routing. And finally, we'll look at the challenges and global impact.
So here's a question for you. How do thousands of totally independent networks actually form one unified internet? It's a great question because it completely shatters a really common illusion. The internet isn't some single giant monolithic thing. It's actually this massive patchwork quilt of completely independent systems that have somehow negotiated these really complex agreements to work together. And figuring out how they pull off that negotiation, well, that is the secret to understanding the internet itself.
All right, let's kick things off with Section 1, the network of networks.
Okay, so here is our absolute foundational building block. We call it the autonomous system, or AS for short. Think of an AS as a massive collection of IP networks and routers, all under the control of a single organization using one common routing policy. To keep all this organized on a global scale, every single one gets its own unique tag, an autonomous system number, or ASN. It's kind of like an independent country or a specific postal region. Each one has its own internal rules, its own protocols, and they operate totally on their own. But for the global web to actually do its thing, these massive, independent digital countries need a super reliable way to talk to each other and exchange data.
Which brings us to Section 2, BGP, the global diplomat. So how do these independent countries actually communicate? They use BGP, or the Border Gateway Protocol. If an autonomous system is an independent nation, BGP is the universal diplomatic language they all speak. It negotiates the borders, it establishes the trade routes across the web. Because BGP is specifically engineered to juggle these incredibly complex routing decisions between totally different administrative domains, it is literally the undisputed heavyweight protocol of the internet.
Okay, let's dive into this. Section 3, the mechanics of routing.
Let's walk through the actual step-by-step journey of a data packet here. Step 1 is BGP peering. This is where routers sitting right at the edges of different autonomous systems establish direct TCP sessions with each other. It's basically a digital handshake across administrative borders. Then, step 2, route advertisement. Once an edge router learns a new internal route, it essentially shouts it out, advertising those paths to its BGP peers all over the globe. Step 3 is all about keeping things from breaking, using something called the AS path attribute for loop prevention. And finally, step 4 is route selection, where these routers make incredibly fast, highly calculated decisions to pick the absolute best trajectory for your data.
Now, I want to zero in on step 3 for a second, the AS path attribute, because this is absolutely crucial. As these network prefixes get advertised across the internet, BGP actually attaches its ASN to a running list of every single system that route has passed through. It's leaving a digital breadcrumb trail. And without this, network topologies could easily get trapped in these infinite, endless routing loops. We'd see devastating routing storms that would literally crash huge portions of the internet. So by just checking that AS path list, a BGP router instantly knows to drop any advertisement that already has its own ASN in it. It's a remarkably elegant way to gracefully dodge a total catastrophe. Right, so what happens when a router gets multiple different paths to the exact same destination? Well, BGP doesn't just guess. It uses a really strict deterministic process. These routers are constantly comparing a bunch of attributes to pick the optimal route. For example, they'll look at the AS path length, usually preferring the route that hops through fewer networks, but they heavily weigh that against internal metrics, like local preference. And the crazy part? This complex, calculated decision-making is happening continuously, in fractions of a millisecond, for hundreds of thousands of routes, all at once.
And that brings up a really important point. Picking a route isn't just a simple matter of pure speed or finding the mathematically shortest path. Out in the real world, organizations lean heavily on policy-based routing. Network admins are setting up incredibly strict policies to dictate exactly how traffic enters and exits their AS, and they're basing this on real-world business factors. We're talking transit costs, peering agreements, performance metrics, and of course, security needs. So inter-AS routing really gives these engineers a massive degree of flexibility and control over how global data is exchanged.
Let's zoom out a bit for Section 4, challenges and global impact. When you take all these localized, micro-level peering agreements and scale them way up, what you get is the internet backbone. The core of the internet is built on these mind-bogglingly fast, high-capacity links, We're talking terabits of data per second getting shoved through transoceanic fiber cables connecting these massive autonomous systems together. And this entire Tier 1 infrastructure, it relies entirely 100% on BGP to keep all that traffic flowing smoothly on a global scale.
So if we summarize the big picture here, we see a really clear chain reaction. BGP's policy flexibility is awesome because it gives individual organizations immense control. But propagating all those complex policies across the globe introduces massive scaling challenges for internet service providers. I mean, they're managing just colossal routing tables. And at insane scale, it amplifies some pretty critical security considerations, which ultimately turns these deeply technical routing mechanics into major, high-stakes issues of global internet governance.
Because BGP is the protocol defining these cross-border data flows, its built-in vulnerabilities are a huge governance headache. Historically, this protocol ran largely on trust, which, as you might guess, leaves it wide open to manipulation. For example, if an autonomous system just misconfigures a single router, it can accidentally advertise the wrong IP prefixes to the world. We call this BGP route hijacking. When that happens, massive chunks of global web traffic get abruptly intercepted or detoured through totally unintended geographic borders. That means widespread outages or, even worse, severe interception risks. Securing BGP is absolutely a top-tier priority for network operators everywhere.
So, as we've seen, autonomous systems and BGP work together beautifully to create the very architecture of the modern web. But it leaves us pondering a pretty provocative reality. BGP effectively holds the entire internet together. But with these known inherent security vulnerabilities, just how safe is our digital backbone really? It's this fascinating, fragile, yet absolutely critical piece of infrastructure, and it demands constant, around-the-clock vigilance from the folks managing our digital borders worldwide.